Have you ever wondered how a machine learning model that boasts 99% accuracy can still be a complete and total failure? Well, the secret lies in this constant, behind-the-scenes tug-of-war, the bias-variance trade-off. Seriously, understanding this one concept is the key that separates a model that just looks good on paper from one that actually works out in the real world.
Oh, you know the feeling. It's a classic story for anyone in data science. You've spent hours, maybe even days, training a model. You're watching the accuracy climb, the loss is dropping, everything looks perfect. But then, the moment of truth arrives. You feed it new, real-world data, and it just completely falls apart. It is an incredibly common and, let's be honest, super frustrating problem.
And this is why. Over here on the left, you've got the training phase. It's a clean, predictable sandbox. But on the right, you have the messy, chaotic, unpredictable real world. What happened? Well, your model didn't actually learn the underlying rules. Nope. It just memorized the answers to the test you gave it. This failure to generalize is the absolute heart of the problem. And it's all caused by two invisible forces pulling your model in opposite directions. To really get a grip on these forces, let's use a simple but really powerful analogy I like to call the archer's dilemma.
Okay, so first up, we have bias. Picture an archer whose arrows are all landing in a nice, tight little cluster. That's great precision, right? But the entire cluster is way off in the corner of the target, nowhere near the bullseye. That's high bias. Your model has some flawed, overly simple assumption, and it's being consistently wrong in the exact same way over and over again.
Now for the second force, variance. Imagine the archer's arrows are now scattered all over the target. I mean, they're everywhere. A few might land near the center by pure chance, but most of them are way off. There's zero consistency. That's high variance. The model is way too sensitive. It's reacting to every tiny little fluctuation in the training data, including all the random noise. It's completely unpredictable.
So what's the goal here? The dream scenario? You want the best of both worlds. Of course, low bias and low variance. All of your arrows are tightly grouped right in the dead center of the bullseye. Now that is what a great, reliable, and accurate model looks like.
So let's put a more formal definition to that. Bias is basically the error you get when your model's assumptions are just too simple. It's like trying to predict the stock market using only the day of the week. You're ignoring so many important, complex patterns that your model is just fundamentally flawed from the get-go.
And variance? That's the error you get from your model being too sensitive, too complex. A high-variance model doesn't just learn the important signals from your data, it starts memorizing all the random meaningless noise, too. And that's exactly why it looks like a genius on the data it's already seen, but fails miserably on anything new.
So these two problems, high bias and high variance, they lead us directly to the two most infamous traps in all of machine learning, underfitting and overfitting.
This table really breaks it down perfectly. Over on the left, you have underfitting, which is caused by high bias. The model is just too simple, so its accuracy is low everywhere, on both the training data and the test data. It failed to learn. But on the right, you've got overfitting, which is driven by high variance. Here, the model is too complex. It gets an A+ on the training data, but that amazing accuracy completely collapses as soon as it sees new test data.
And here is the absolute key, the most important takeaway. This is a trade-off. You can't just get rid of one without affecting the other. They're connected. As you make your model more complex to try and reduce its bias, its variance will almost always creep up. And if you simplify your model to fight variance, you're probably going to increase its bias. Finding that perfect balance is everything.
You know, this whole relationship can be summed up with a pretty neat formula. A model's total error is basically made up of three parts: its bias, its variance, and this third thing called irreducible error. Now that last part, that's just the random noise that's naturally present in any data set. You can't do anything about it. Your job as the data scientist is to tune your model's complexity to find that sweet spot that minimizes the sum of bias and variance.
Okay, so that's all the theory. But how do we actually fix these problems in the real world? Let's dive into the practical toolkit for finding that sweet spot.
First things first, let's tackle the underfitting problem. So what do you do when your model is just too simple and it's consistently getting things wrong?
When a model is underfitting, you gotta ramp up its complexity. This could mean switching to a more powerful algorithm, like going from a simple linear model to something like a random forest. Or you could engineer more features to give the model more information to learn from. You could also reduce its regularization. Think of regularization as a penalty you apply to keep the model from getting too complex. So by lowering that penalty, you're giving the model more freedom to learn.
All right, now for the other side of the coin. Your model is a straight-A student on all the practice tests, but it completely bombs the final exam. How do we fix that high variance and overfitting?
So here, we pretty much do the opposite. The single best fix, almost always, is to get more training data. But you can also simplify your model, maybe increase that regularization penalty to discourage it from getting too complex, or use something called ensemble methods. That's just a fancy way of saying you combine the predictions of several different models and their teamwork helps cancel out each other's individual errors. You see, at the end of the day, this whole thing is an art of balance. And let me tell you, getting this right isn't just some abstract technical challenge. It has massive, real-world consequences. I mean, just look at this gap. A model with 98% training accuracy looks incredible on paper, but when you find out its real-world accuracy is only 68%, that model isn't just unreliable, it can be actively dangerous.
And just think about what's at stake. In medicine, an overfit model could wrongly tell a healthy person they have cancer. An underfit model could miss a real diagnosis. In finance, an underfit model could approve a bunch of disastrous loans. Getting this balance right is absolutely critical.
It really all boils down to this one simple, elegant truth. The goal isn't to build the simplest model you can or the most complex one. The goal is to build the model that finds that perfect point of equilibrium, that sweet spot between learning too little and learning way too much.
So I'll leave you with this question. The next time you're looking at one of your models, ask yourself, is it a sharpshooter, consistently and accurately hitting the bullseye with low bias and low variance? Or is it just another archer, shooting completely in the dark? Because mastering this trade-off is how you'll finally, truly know the answer.